Hi, welcome to this Vampire Workshop tutorial on longitudinal spin dynamics in atomistic spin models. So just a quick note before we get started. If you wish to try out anything that I do in this video, you will be able to get a copy of the source code in the link that I've provided on this slide. It is currently not incorporated into the official Vampire develop branch. However, in the short term, hopefully it will get incorporated soon. We are working on it at this moment. So just to quickly go over some background and some motivation behind what is the modeling of longitudinal spin dynamics and why it matters. So the current integrator schemes that a lot of people are familiar with in atomistic modeling is the Landau-Lifshitz-Gilbert integrator and the Monte Carlo integrator. So while they work rather well for a lot of systems, the way that they model spins is that they only allow motion in the transverse space, meaning that the length of your spin is not allowed to vary at all. So as I mentioned, for some systems this is fine. However, in systems where there's a lot more induced moments due to exchange, for example, this doesn't quite give you the full picture of your system. So what we have implemented in Vampire is two new integrator schemes that include longitudinal motion. So not only are the spins varying in the transverse degree of freedom, they are also varying in their spin length. So the goal is to essentially be able to get a more physical picture of some systems, every system, given that we are now able to model both the transverse rotation of spins and also the longitudinal changes in spins. So just if you wish to do some further reading on this topic, I've included 3 papers particularly on the topic of longitudinal spin dynamics and what led up to the implementations that you will see in this video. And if you wish to learn a bit more about Vampire, more in depth, then I've also included the main paper on Vampire. So, to get started on longitudinal dynamics, when we consider an atomistic system normally, we would think about a total Hamiltonian that describes the energy of our system. So conventionally, you would have your exchange, anisotropy, and applied fields in a very typical fashion. And the important thing here is that the spin vectors, in this case, refer to the unit vectors of the spin. So this means that there is no contribution whatsoever for the spin length, so the longitudinal component. It's purely the transverse movement that matters here. So what we can do to start introducing longitudinal degrees of freedom is to extend this Hamiltonian via what is known as a Landau Hamiltonian that has 3 material-dependent coefficients that allow for a dependency with the spin length of the system. So it basically allows for an energy variation with respect to spin length. And to aid the visualization of this, I've included an example for BCC iron. So you can see, for example, that at the lowest energy point, where the potential well is at its lowest, you will see that the spin length is approximately centered around 1. So this means that at an equilibrium state, where, let's say, temperature equals 0, your spin length will be equal to 1. And as you increase this temperature, you're able to explore more portions of this energy landscape. So this means that at equilibrium, you won't see a lot of change in the spin length, but as you increase your temperature, you will see more rapid changes in your spin length depending on your system. So in the case of iron that I show here, it's actually a rather stiff spin, meaning that the longitudinal changes are not that significant even at higher temperatures. However, it's a good example to illustrate the model as a whole. I've also included the exchange and exchangeless versions of this curve. This is because, as I mentioned earlier, the point of the Landau Hamiltonian is that it is appended to the total Hamiltonian. So the effective potential well that you get is constantly shifting based on the exchange energy and all sorts of other energies based on the anisotropy and applied fields, for example, that are in your system in addition to the longitudinal components. So here you can see a table for 3 typical materials that we have run tests on, and you will be able to find the A, B, and C coefficients of iron, nickel, and cobalt here. So just to kind of talk a bit about the standard LLG integrator, and then we will segue that into the longitudinal spin fluctuations version of this. So just a quick recap. The LLG integrator uses a computed delta S to model the precession of a spin based on an effective field that acts on it that depends on the total Hamiltonian of the system. So this is perfectly fine. Once again, this will model the movement of a spin on a unit sphere where the spin length is constrained to 1. So we can now include the longitudinal components that I showed earlier in the Landau Hamiltonian in our effective fields by decomposing the Landau Hamiltonian into x, y, and z components of the effective field. And we can do this by taking a look at the earlier identity and realizing that we can differentiate the total Hamiltonian with respect to the spin vector to get the effective field contribution. And so that's the result of this here. So in addition to a minor change to how the thermal noise is included in our integration steps, we are now able to model the spin rotating on a unit sphere, but also having its length vary across this time. So for a standard LLG integration, I've included an illustration here which demonstrates that the spin length is constrained to 1, and you're essentially only seeing movement in the transverse space, whereas once you include longitudinal spin dynamics, your length is also allowed to change. So to talk a bit about the LSF, so the longitudinal spin fluctuations and Monte Carlo-like integrator scheme. The standard Monte Carlo, for example, you would simply make changes to the transverse component of your spin vector and assess based on a Boltzmann probability whether or not it should be accepted as the new spin position or to reject that new suggestion. Now, once again, this will conserve the spin length exactly to 1. However, in this model, where we want the spin length to change, we are allowed to include longitudinal contributions via the modified total Hamiltonian that I showed earlier. So this time, when you evaluate your probability of accepting or rejecting the move, it includes the energy contributions from the Landau Hamiltonian. So this means that there is a bit more inefficiency because you are sampling a larger amount of phase space. However, this now allows us to model longitudinal motion as well, which is our goal. So there is a slight difference to the way that we have decided to look at the LSF model compared to the papers that I've included at the start of this video. The biggest difference is that when we were implementing this, we realized that the exchange and anisotropy, and by extension the applied fields, they have a significant effect on where your spin length minima is located at equilibrium. So there will be many instances, for example, where you will give the Landau parameters, the A, B, and C coefficients for a given system. And once you increase the size of the system, for example, meaning that you have larger exchange contributions, your new spin length minima with the exchange contributions may not line up to be exactly 1 anymore, because it's now a different amount of exchange contribution than when you first parametrized your system. So in order to combat this, we constantly apply a refitting to the coefficients if this deviation from the 1 spin length equilibrium point deviates too much. So the way that we do this is that we have a typical set of A, B, and C parameters that we start with for any material we're looking at. And if the deviation of the spin length is, for example, 1.1, meaning that my magnetization at equilibrium would also be 1.1, which obviously is not quite physical, what we would then do is we would simply introduce a D coefficient, which then shifts this curve back to exactly 1, and then you would embed the effects of that D coefficient into a new set of A, B, and C coefficients. So you will still only have A, B, and C, however they have effectively been readjusted to accommodate for a difference in exchange energy, or total energy for that matter. So the exchange and anisotropy between systems can greatly vary on how big your system is, whether you have introduced any defects, and what kind of nearest neighbor configuration is available to your spins. For example, if you are at the surface of a structure, you will notice that there are less nearest neighbors than at the very bulk, and this obviously will have an effect on your spin length minima, so the equilibrium position of your spin length, which is where something like this might need to come into play. So currently there is no elegant solution for this, and if you wish to use these integrators to model systems of your own, then we would suggest that you use the parameters I have provided in the table in the earlier slide, and based on that you can do a set of readjustments if necessary by readjusting your spin length minima to 1, and then once again to then refit to those new parameters afterwards. However, this isn't necessary for every single different system. For example, if you're looking at BCC iron, but your system size is, let's say, 4 nanometers, and then you're doing one which is 8, it's very likely that you won't need any sort of readjustment. It's only when there are much more complex introductions to these systems that this becomes a bit more of a complex issue. So now to get onto the vampire, how to use this integrator scheme. So once you have the source code, and once you have compiled the source code according to the manual, which is still valid, you will simply define a system that you wish to simulate. So in this case, I'm showing an example for BCC iron, simply just a cube, 6 nanometer cube of BCC iron. And I have included a material file, which I will show momentarily. However, the important thing is if you wish to use either of the LSF integrators, you will have to specify this in the sim integrator portion of the input file, and you will be able to choose either from LSF or LSF-MC. LSF is the LLG-like variant of the longitudinal spin dynamics model, and LSF-MC is simply its Monte Carlo counterpart. A quick suggestion as well is if you wish to use the LSF-LLG integrator scheme, we suggest that you restrict your time step size to 10 to the minus 16, or 0.1 femtoseconds, as it has a strict dependence on the time step being that large. If you deviate to 10 to the minus 17 or minus 15, although it will work for some systems, there will be cases where it will fail to properly model the spins. It should also be noted that if you wish to output your spin length values in your simulations, you will need to include a new output function that gives you the value of your spin length at every time step or every temperature increment. And you can see an example of this on line 48, where it says output material mean spin length. So now onto the material file. So the only thing that you will need to specify in addition to, for example, the exchange and anisotropy, is the 3 Landau coefficients, the material dependent coefficients, in units of joules. So as I showed earlier, just a quick recap, these 3 coefficients correspond to the without exchange dotted line on the figure on the screen. Once you include the exchange contribution that you specify as the exchange matrix that you can see at the very last row of the material file, that is how your spin length curve will shift to the with exchange description of the spin length potential well. So once your simulation has finished running, you will notice that there will be outputs for the normalized magnetization of the system and also the spin length of the system. So you can see that while normalized magnetization gives you a fairly expected answer, the interesting part of this is that you will now be able to see and model the spin length of your system. So you can see that in the example of iron that I have just gone through, the spin length actually doesn't change that much, even towards higher temperatures, and that's simply because the potential well associated with changes in its spin length is extremely steep. So it's very difficult to put energy into the longitudinal degree of freedom and expect any changes. To share an example that is a bit different to iron, where you do see some more interesting behavior, is, for example, nickel, where I have decided to simulate this according to the parameters I've provided in the table earlier in the video. You can see that, once again, the normalized magnetization is rather standard. However, the spin length starts to yield some fairly interesting results, and this is simply due to nickel's potential well being much more easily changed because of any sort of external exchange field or anisotropy. So in this case, this is simply bulk nickel. You can see that in the presence of an exchange field, the spin length is rather constrained to a decreasing profile. However, once it reaches its Curie temperature around 450 to 500 Kelvin, you can see that the spin length starts to shoot off in the increasing direction. Thank you very much for watching. I hope that this video has been useful. If you wish to learn some more about Vampire, or to check out any updates or any projects that we have going on, please feel free to visit any of these websites that I've included here. Additionally, if you wish to watch any more tutorials or updates, please check out the other videos on this channel. Thanks for watching.